All right, geometry kids, welcome to the second lesson. This one, believe it or not, is going to be about coordinates. We've been talking about parallel and perpendicular lines and a transversal and how that all interacts. Now we're going to start talking about that with the coordinate system. Because parallel and perpendicular have something to do with something you've already learned about. Now coordinates can happen in one dimension, like a number line, which you don't really think about very much anymore. You probably did a lot of this in elementary school. And coordinates can also happen in two-dimensional systems, like x and y plane, which you're very used to in last year. On the number line, distance is really easy to identify because all you have to do is subtract the coordinates on a number line. So I've just slapped a little number line up here. For example, if you had to find the distance between, let's say we had a point right here, let's call it, that's a point. Let's call that A, and there's another point up here somewhere. We'll call this B. The distance from A to B is not really that tricky to figure out. It's the distance from 1 to 5. All we do is subtract 1 and 5, and we find out the distance is actually just 4. On a coordinate plane, that's a little trickier. I hope you can read these words with this graph paper behind it. You have this more spread out on your worksheet, so it shouldn't be too bad. The length of the segment AB in this coordinate system, where this is still 1 unit of length, just like the distance from 0 to 1 on the number line there. If we're going to use those units to measure this distance, it's a little tricky because, like, going right up this graph paper here, this is actually a little farther than 1. Each one of these is a little farther than 1. It's weird because it's diagonal. You know that diagonally going across a field or something is kind of a shortcut from doing this. So it's unusual to try to find this. But it's defined here. We use the Pythagorean theorem to come up with a distance formula. Okay, so you probably remember measuring things this way in Algebra 1. We called this number the rise. How much is B higher than A? We call this the run. How much farther is B from A, kind of in an east-west direction? So there's kind of an x-axis kind of measurement spread, and there's a y measurement spread there between the two coordinates. If I do that, and this is sorry about that. If I do that, the beauty of the coordinate system is those things will always be perpendicular. The left-right direction and the up-down direction are ensured as perpendicular because of the way the coordinate system line up. This 6, 2 and this negative 6, 3, they tell us how that works, or how far apart those are going to be. Then if I know how far that is and how far that is, then we just do our good old-fashioned a squared plus b squared equals c squared Pythagorean theorem. I'm sure you know all about that. So let's try to find the distance here. I'm going to change colors here. The north-south distance between A and B, you could count it here on the number or on the coordinate grid. You could just count these squares and see how far, that's hard to do in this technology, how far up that is. Or you could get fancy and subtract. This coordinate B has a height of 2. This coordinate A has a height of -3. Notice this is at -3 on the y-axis. This is at 2 on the y-axis. This distance here, this little y span, this is a distance of 5 from -2 down to, from +2 down to -3. Or you could count 1, 2, 3, 4, 5. The distance down here from this position where A is to this position where B is, in the left-right sense, is from A's -6 to B's +6. That's a distance of 12. Of course, you could count that too also, blah, 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 and you'd find out that there's 12 here. There's 12 span there. So I have this little right triangle that's 5 on this side and 12 on this side, and you did this kind of thing, I don't know, probably 2 years ago in some middle school math class or somewhere. Anyway, when you have a right triangle, you know that a squared plus b squared equals c squared, and this is what we're looking for, this hypotenuse. So we'll be able to do this fancy thing and solve for c, and we'll find out very quickly that c, well, if I add those up, that's going to be 169. In other words, c is 13, exactly. We'll do more examples of this in class. You know what? I never looked at the end of this thing. What did it say at the end here? Find the x value and the y value, substitute everything. Okay, fine. Yeah, I did exactly that. It says that right there in number 1, 2, 3. Okay, great. Or if you really love formulas, and I tell you what, this is one of my least favorite formulas in life, and I'm a math teacher. Oh my gosh, do I hate this formula. Isn't this a big pain? This is, if you want to slap all those numbers straight into one formula and put your head down and just put it in the calculator and trust the calculator blindly and get a distance, that's actually what just happened to all these numbers. The 6, the 2, the -6, the -3, into one great big formula that's going to crank out a 13. But oh my gosh, I've seen this year after year. I think it's a lot easier for students to plug it into a Pythagorean triangle and think about the 5 and the 12 and do the Pythagorean theorem. There's so many things that can go wrong in this. I don't even want to. I don't want to talk about this. Let's just like pretend this never happened. Let's just continue to use Pythagorean theorem. I'll make another example. This isn't on your sheet, but let's just do it. If you were given coordinates like, well, you know what? There's 3 more examples coming up. I'm going to do it right now anyway because you can use it. All right. 1, -4. I want to find the distance from 1, -4 to -2, 3. How do I do that? Well, I very crudely draw, because it doesn't have to be perfect. I just have to get a little bit of visual here. I very crudely draw these coordinates. 1, well, that's x-axis. -4, it'd be something like down here. And the other one, remember, that's 1, -4. And the other point, -2, maybe I should have drawn all these in. -2, 3 is something like up here. I want to know what's this distance here to here. Well, let's build this into a right triangle. I'm going to write on my 4 a little bit. Think about that being part of a right triangle. If you can't see that right triangle, I can make it a little more visual here. Oh man, this is hard. If you ever had to look at the technology I got to use to make this, you understand why it's so amazing. All right, so I have this little right triangle here. How long is this side? And how long is this side? I'll want these later for another calculation anyway, so it's really good to do this rather than that whole crazy formula up here. Gosh, I hate this formula. I hate it so much. Okay, so from 1 to -2 is a distance of 3. I could count that on real graph paper. I could go, okay, 1 to -2, how far is that? That's 3. And how far is it from -4, the height down here, to the height up here? That's from -4 to +3. You can look at that over here too. One of those dimensions on this triangle was the distance from 1 to -2. The other one was from 4 to -3. This space was 3. This space was 7. This is 7 right here. So I know 7 and 3 now, and here they are again. 7 and 3 are the sides of my right triangle. I know 7 squared plus 3 squared equals that distance squared. And no, I can't say this is 10 squared. Get that out your head right now. That's 49 plus 9. So d squared is some gross number like 58. And so d is actually just the square root of 58, and don't let that scare you. You should be happy leaving it like that. I don't want to get my calculator out and figure what that is. I know it's the square root of 58, and I lead a pretty full life thinking that's how it is. Okay, midpoint. It's the other thing we're doing today with coordinates. If you had to find the midpoint back on coordinates like this, if this is your line segment, if your line segment goes from A to B, that line segment was 4 long, finding the midpoint on that isn't so bad. We're just basically cutting that in half. Cutting 4.5 is 2. Well, 2 is not the midpoint. 2 tells you the length from the end to the midpoint. There's 2 here, and there's 2 here. So that says this is the midpoint. The midpoint's at 3. 3 is the average of 1 and 5. So what we could have done to figure out that is we could have taken 1 plus 5 and divided by 2. And we'd get the average spot on the number line there, and the average spot on the number line between 1 and 5 is 3. And that's exactly what we're going to do with 2 coordinates. It's exactly what just happened here. So, need another example? Need an example? I haven't given you any examples. Okay. So if you had 2 coordinates, we'll use the same ones we just did. Why not? We'll use the same points. We just use these 2 points, 1, -4, and -2, 3. You have those on your paper already. So we'll say 1, -4, what did I say? -2, 3. Those are the endpoints of a segment. What are the midpoint? What's the midpoint of that thing? Well, just this one I actually don't mind just plugging that in. I need to find the point that's halfway between 1 and -2. You know what? I'm going to draw it again. 1, -4 was down here somewhere. And -2, sorry, this is really slanted. -2, 3 is up here somewhere. If I use actual graph paper, it would look a lot better. I'll do that in a second. It's just preliminary. So I'm talking about this segment here, just like last time. I want to locate the midpoint. Like, where exactly is the midpoint of this thing? Well, it's halfway between this position of x and this position of x. And it's halfway, the left-right distance, it's halfway on the left-right trip. And it's halfway on the north-south trip from -4 up to +3. Halfway along the trip from 1 to -2, well, that's just 1 plus -2 divided by 2, which is -half. Is that right? I did that right? 1 plus -2. Okay, there's a lot of these little tiny integer calculations. And halfway from -4 to +3, this is going to look very similar, I think. -4 and +3, if I add those up and divide by 2, oh, guess what? I get the same thing. That's very unusual. I just made up an example where that's the y-coordinate and that's the x-coordinate. This little point here that I was trying to locate here, it's at -half. -half. Crazy first example. All right, well, there's more coming up. Slope. All right, this is the last concept of the day, pretty much. Slope was an indication of the direction that a line is going on the coordinate plane. So this line back here I was looking at a second ago. If I was going to describe the slope of this, I want to be able to convey to people the fact that this is going downhill rather sharply. There's lines that could be sitting kind of horizontally. There's lines that could have kind of an uphill kind of slant, and we want to be able to quantify that. Whoa, sorry about that. So this page on slope, again, this is review. You should have seen this before. Slope, if I was looking at a segment that was kind of sitting that way on the coordinate plane, I need to take rise divided by run. And that's what we've been looking at here with this distance formula. Rise was kind of a quantity like that. How much higher is one point than the next? And run is how much farther to the right is one point than the next. So this up-down comparison and this left-right comparison, we're using those in lots of ways today. So this one I would call rise, and this one I call run. And when I divide rise divided by run, I get this formula for slope. Slope is positive when you'll find in these fractions, slope is positive when it's going in this sort of uphill direction, left to right. It's negative when it's going in this downhill direction, left to right. I would write these on my sheet if I were you. It's a zero slope line if it's perfectly horizontal. And it has no slope or undefined slope if it's perfectly vertical. We'll talk about that in class. It has to do with whether or not there's a zero in the fraction. A zero on the top of the fraction is okay if this happens. A zero on the bottom of the fraction is not okay when this happens. Other than that, we're going to get stuff like this. I think you really do need to remember, for estimation purposes and at the end of the problem to know if you're right or not, or if your answer is crazy, it's a good idea to memorize this. Left to right, if the line's going uphill, it's positive, and if it's going downhill, it's negative. One more, then I'll make another video about some examples. So why are we caring about slope in this chapter? I thought we were doing parallel lines and planes and everybody was happy. Well, slopes in this chapter are here because this is where we finally get to perpendicular and parallel. We can talk about perpendicular and parallel if we know about slope. If they have the same slope, they're parallel. So two lines have the same slope or parallel. That's pretty easy to remember. Again, we'll show it in the examples. For lines that have perpendicular slopes, they have to have slopes that multiply to make -1. So if I had slope of one line, I'll just say this. If the slope of one line is -3/4 and the slope of another line is +4/3, guess what? Those are perpendicular because -3/4 times +4/3 happens to be the magic number -1. Another way to say that is that they're negative reciprocals of each other. So you look at numbers like this, -3/4 and +4/3, they're upside down from each other and one of them is negative. If they're upside down and negatives of each other, they'll be perpendicular. Okay, I just got to the example stuff coming up next, so I'm going to stop this and call it part 1, and then I'll do part 2 separately.